So we know that sound travels as a wave. A wave's an oscillation that carries energy. And in sound waves, the particles oscillate in the same direction as the wave is traveling. So because the particles are oscillating back and forth in the direction of the wave traveling, it means that we have periods or areas where all of the particles are very, very closely packed together. And then they spread out. And then they pack closely together again. So we have areas where the particles are packed together closely, compressed, and there's areas where they stretch out, and there's areas where they compress again. So remember, what happens is that the particles are oscillating back and forth, and they're coming in contact or pushing the particles next to it and transferring the energy. So it goes as a wave of compression and stretching out, and compression and stretching out. So we need to go ahead and label these different parts of the wave. This part is easy. It's called a compression. Now, a word that you haven't probably heard before is the part where it's stretching out is called a rarefaction. So sound waves, longitudinal waves, they have a series of compressions and rarefactions as they travel. Now, sound waves are often represented to look like our typical transverse wave like this, because it's easier for us to look at the properties. It's easier for us to visualize it, say, on an oscilloscope. So I'm going to show you how this translates to a wave diagram like this. So basically what we're saying is that when it's under compression, it's on this side of the midline, and when it's in rarefaction, it's in this side. Okay, so we start by being in compression, and then at this point we go into rarefaction, and then at this point we go into compression, and then we swap over to rarefaction. Okay, and so that's what we see here. This wave can be represented like this. Now, so what we're able to do then is we're able to measure the amplitude, which is the height of the wave. So this is the amplitude here. We're able to measure the wavelength, which is this distance here. We're also able to measure the frequency. If we know how long it took for these waves to travel past, say it's 1 second, we can say that's one wave, two waves, and another half, so 2.5 waves per second, or 2.5 hertz, 2.5 hertz. So if a sound wave is represented like this, just be aware that it is still a compression wave. It is still a longitudinal wave. It's just that this is a nice, easy way for us to visualize it. So let's just have a look at some properties of some different waves and see what effect that is going to have on the sound. So I'll draw a wave first of all. Okay, now, so that's one wave, and let's compare it to another sound. Okay, so there are two sounds. So what can we see here? First of all, the amplitude, remember the height of the crest. So we've got this one here, the amplitude here versus the amplitude here. We can see that the first wave has a much higher amplitude. So if these were sounds, which one would have a higher volume? So we've got higher energy, higher amplitude, so it's got a higher volume. Now let's have a look at the wavelength. Remember, the wavelength is the distance between two of the same point. Often helpful to do the peaks or the crests. So that's one wavelength compared to one wavelength here. So this second wave has got a much longer wavelength than this one. Is a shorter wavelength. How does that relate to frequency? You know, frequency is number of waves per second. So let's see, in this trace here we've got 1 and 1.5 waves. I'm just going to extend this one a little bit more. So here, let's say we've got 1.5 waves in this period of time, and here we've got 1, 2, 3, 4.5 waves. So this one has got a higher frequency, much higher frequency. Now, how is frequency related to sound? Well, that's actually the pitch of the sound. High frequency is high pitch. High frequency is high pitch. Low frequency is low pitch. So when we have more waves, or it's a shorter wavelength, higher frequency, we have a higher pitch. And when we have longer wavelengths, we have a shorter frequency or lower frequency, and it's lower pitch. So that's how the properties of waves relate to the sound we actually hear.